welcome to the Spatial Structures Movers and Shakers interview series as we look ahead to the ISS Annual Symposium and Spatial Structures Conference taking place at the University of Surrey in August 2021. My name is Mark Richardson and today I'm joined by Olivier Baverel, who is a professor at the School of Architecture Grenoble and a professor at the Ecole de Ponts Paristech. Olivier is also editor-in-chief of the International Journal of Space Structures, and Olivier is also a member of the IASS Executive Council, as well as being a member of the Scientific Committee for the 2021 conference. Olivier, thanks very much for taking the time to join us today.
Hello, Mark. Thank you very much for this interview.
No problem. It's a pleasure to have you on the Movers and Shakers interview series. And we start our interviews by asking our guests about lockdown. How has lockdown been for you in France?
Well, I'm quite used to work remotely as I work in Paris and in Grenoble. And for the lockdown, I was in the house. And so my life was not so difficult.
Sounds like you're well versed in remote working.
No problem working and no problem working remotely. And it was sunny. And we were allowed to walk 1 kilometer around our place. And there are already nice mountains at less than 1 kilometer from my home.
That sounds good. Good to have access to that at least. And we also begin our interviews by exploring the career paths our guests have taken. Perhaps you could give us a brief overview of your own career journey, Olivier.
Yeah, so I started my studies of engineering in France, and I had the chance to get quite an important grant from Europe to carry on in UK. So at that time, these things were possible. People believed in Europe. So that's true now. And I had the chance to carry on doing a PhD in the Space Structure Research Center in Surrey.
That's great. And as you've alluded to there, you're obviously an alumnus of the University of Surrey. Could you share with us your experiences of perhaps working alongside Professor Nushin and Professor Jerry Park?
Yeah, so, well, I worked mainly with Professor Nushin, and I also had some exchange with Jerry, who's a really nice person, and it's more or less him who allowed me to do my PhD in the Space Structure Research Center. And after I worked mainly with Professor Nushin, who was really ahead of his time, because he started to work on the complex geometry configuration back in 1984. So more than 20 years ahead of anyone. And he developed some tools and also some algebra specific for creating form finding of space structure. And I try to carry on, and I will show it in my presentation. But the experience was fantastic. Professor Nushin is an extremely good scientist and someone extremely nice, and spend a lot of time with his PhD students. And I told him I will try to do as nice as he has done for me. Well, now you have to interview my PhD students if I've done it.
Okay, well, look forward to that, Olivier. And maybe you could tell us a bit more about your experience of being editor-in-chief of the International Journal of Space Structures. What lessons have you learned from being in this position?
Well, it's extremely interesting. We see plenty of different topics coming from all over the world. And but it's really inspiring, but it's pretty tiring to do this job, because you have to think about it every day. You receive email from anyone at any time. So it's not an easy job, but it's extremely interesting it shows you what people are producing in terms of research in space structure almost every day.
Fantastic, thanks for that, Olivier. Well, I'm now going to hand over to you for the middle section of our presentation, where Olivier will be taking us through the section entitled Your Space, Your Structure, and Olivier will be presenting on a topic relevant to spatial structures of his choosing. So over to you, Olivier.
Okay, so I share my screen, and I hope you've got it. So the title of my presentation is Make Structure, Space Structure Affordable. And before this, I would like to show this graph, which is coming from a publication from Catherine Devol, who showed the material quantity per seat for different stadia all over the world. And you can see, for instance, the stadia of Olympic Stadium of Beijing in 2008, and the one in London in 2012. And you can see clearly that the material quantities per seat created is 10 times bigger for the one in Beijing. So we clearly see that if we're living in a world with limited resources, we clearly have to think in terms of how we can build in a sustainable manner. Because clearly the stadium from Beijing, even if it was nice looking or whatever, it's by far consuming too much materials to be created. So we need to build in a sustainable manner, but the big question is what is the definition of being sustainable? So that's what we try to work on in the IASS working group number 18, which is called Life Cycle Design and Assessments of Shell and Spatial Structure. I co-chair this working group with Corentin Fivet. And of course, in this working group, we work on the life cycle analysis of space structure, which look at not only at CO2 emission, but also at 17 other parameters that create some pollution. But it's not only this, I think, because life cycle analysis is known. And the question is, how do you adapt it to space structure? So there's a big question about no waste, what we do with upcycling or reusing component resilience. And so this working group will focus on these questions. And at the end, nobody has given us the right to our generation to give waste to the next generation. So we have to really do something. So that was, I would say, the work done with the community of IASS. And I will focus now more on the answers we have to sustainability with my team, which is a broad team, but I will call it Think Shell. And our answers are advances in geometry generation, advances in technology, and advances in material. So I'll start about advanced geometry. And in advanced geometry, I think it all started with this famous project of the Citroën DS, or a famous French engineer called De Castelgio, made an algorithm and invented the CAD drawing. Someone called Bézier, who was working for Renault, popularized the algorithm, and now all CAD drawings are made with this algorithm. But you see a problem in our industry is that we're using a fantastic tool made for automotive industry, but not adapted to our industry. Why? Because in our industry, you draw a surface, but after you put a mesh onto it. And when you give a thickness to the mesh, sometimes it gives you some very pretty complex nodes, like you can see on the right, and very expensive ones. So you have to rationalize the surface you're using to create a mesh that will work. So that's, for instance, here you take the surface, you create the mesh, and then you extrude along the normals of the mesh. And you see on the right on the picture that clearly we have nodes with torsion. So I try to zoom in a bit. We see here is the z-axis of all the beams are not parallel to the normal of the surface. So this makes complex nodes to be built. But in our team, we work on different types of surfaces, and there are some specific surfaces that are easily buildable without any need of optimization. For instance, discrete constant mean surfaces have the properties of being directly buildable. So So here's an example of a constant mean curvature surface with, you see the node without torsions. The element that will cover the surface are made out of planar elements, which are easily buildable. And also on this specific surface, you have only two, well, the thickness is almost the same within the structure. In reality, you have two different thicknesses, but they are pretty close to each other. So almost a constant thickness. So this was the work was done with the PhD of Xavier Tellier. But speaking about geometry, I think it's important also to be able to generate the geometry quickly. And you can see here, there's an algorithm that we developed with the physicist of Romain Ménil called the marionette mesh. You choose two lines, the two colored line on the left picture. And with these two colored lines, by propagation, you can create the picture on the right, which is a surface with only flat panels. But what is interesting is that it takes only 5 milliseconds to create this this geometry. So it means if it takes only 5 milliseconds, then you can do an optimization. And that's the strength of this algorithm. So you have straight a structure which is buildable. And as you have a very quick generation of the structure, then you can optimize it. And here with thousands of examples and some gradient descent algorithm, we managed to lower the mass by 30%. So this is an important point. Now, at the moment, architects are mainly using CAD drawings from the automotive industry. They need post-rationalization to actually be able to optimize just the mesh of their structure, and it's a very long process. And in the manner we propose, we can have something very short. So speaking about technology, in 2017, we built a shell Nexorhead structure. Nexorhead structure are interesting structure because the nodes are blown up, and so they are easily buildable. And the assembly is pretty simple. But it's structures that are mainly bending dominated, so they are not very stiff. But as we mentioned it, it's a shell Nexorhead because in this example, we managed to keep the faces planar. So it means we can put bracing elements that will fill the element, the panel in between the nodes, and therefore you will have a shell behavior. So what is interesting is you take the best of both worlds, I would say. You take the Nexorhead system to get simple technology, and you take the bracing element to get the behavior as a shell. So here's a few pictures, and of course, well, I won't go through the full chart because I don't have the time for it. But what we have used is a specific, we have two robots that can work together. So it's a sort of 13 degrees of freedom system. And in our case, one robot was holding the beam and the other robot was doing the milling. So we were able to mill in any direction pretty easily. Well, it's a simple work. It took a lot of time to manage to show that the robots were in the same world and to be accurate enough. And we have a fantastic team that allowed us to do it. So here's you see a very on-site, a very simple node for the assembly. Now, speaking about material, advanced materials, you know that 3D concrete printing is at the top of the hype curve at the moment. So we worked on it. And at the end, when you do 3D printing of concrete, it's a similar question to brick layering. Instead of having bricks, you have a lace. But at the end, you do layers as you do with bricks. So it means the geometry that you can achieve without formworks at the end have some similarities. You can see here at the end, you have three possible strategies. Is you put your lace on top of one another, either in pure shear, either with a shear and bending, or only bending. And you can see we find some very famous traditional masonry construction. But at the end, we can do something very similar with 3D printing. It's a PhD of Paul Carnot. You can see here, we can do a Nubian vault. On the right side, you see the part of the robot who is printing it, and on the left you see the final construction. So you're able to actually pour fresh concrete without formwork by reusing ancient strategies. Speaking about advanced materials, I think I have another example. Speaking about grid shells, we've been working on grid shell for 15 years. And the new novelty we've done, it was by using glass fiber reinforced polymer. Well, the life cycle analysis is not maybe as good as wood, but what is good with glass fiber reinforced polymer is that you can do a span of up to 15-meter span with only a single layer system. So we made many research on it, and we have done quite a few constructions. And well, I would say the most famous one was the Créteil Temporary Cathedral that was able to host 500 persons. And it was disassembled last year because now they have the new cathedral. And the entire structure was lifted by 2 cranes, 40 tons cranes, in just half a day. So move on to another question of advanced materials. And here, a recent work I did for an association called Architect. So if you look clearly, well, it's a simple truss that we all know. But if you look a bit more closely to these red elements, they are skis. So you have to know that in France, France is destroying 800,000 skis per year. So this is quite a lot of waste. And also it's a very interesting building material, as in, with very good properties, whether composite, glass fiber, carbon fiber. And the idea was to say, how can we reuse it to make new structures? So here's an example. And we hope to build some others, maybe a bit more different from a simple truss. But this was, we had to start with a simple thing to show and demonstrate that it was possible. So to be sustainable, life cycle analysis is not enough. In my opinion, we have to work also with ecosystemic services. And I don't know if you all know about it, but ecosystemic services it's a very complex thing. It's mostly services given by nature to the human. It's either supporting, provisioning, cultural, and regulating. But I've seen a recent publication that was saying, well, ecosystemic services are services to ecosystem. You see that in ancient civilization, there were a reciprocity in between human and ecosystems, and humans were using services to ecosystem, and they were finding a sort of balance in between providing services to ecosystems and system providing services. So by thinking about this, we have built a startup called Urban Canopy. And this startup is reusing the knowledge we developed for grid shells. And they provide sort of artificial trees to be able to set up vegetation to places where nothing can grow, and places where you cannot plant a tree. And this provides some shading and lowers the local temperature, and also provides the ecosystemic services from nature in a city. So to finish my talk, this is my team of ThinkShell, my dear colleagues. You see on the left our ongoing PhDs, and on the right our former PhDs.
Thanks very much, Olivier, for taking us through that presentation. Some very pertinent topics with respect to the future of spatial structures covered there, particularly like the skiing example and the example of spatial structures with respect to inclusion of nature. Very, very pertinent. And that's actually leads nicely into the final section of our interview, which is about the future of spatial structures, and particularly inspiring the next generation, which is the ISS 2021 conference theme. How do you think we can best achieve this aim of inspiring the next generation of people working in the field of spatial structures?
Well, in my opinion, so far we've been designing a structure without thinking about the end of life of it. Now we really have to rethink everything, thinking about the entire cycle of a structure. A structure is not here built for eternity. It has to be removed sometime. Maybe it's on 100 years, but at least we should provide the plans to how to remove it. So I think it's really interesting to see that we're gonna move on to a new generation of building where we're gonna think about the building phase, but also maybe the deconstruction phase, and maybe reuse some of the elements, some elements not reused. And I think it's an immense challenge that we have, because we live in a planet with limited resources, so we cannot take resources up to the infinity.
Absolutely, yeah, I couldn't agree more with you, Olivier. Another interesting topic we've talked about on the series with some of the other guests is spanning the bridge between disciplines related to spatial structures. So as someone with over 20 years of teaching experience in the areas of engineering and architecture, what is your approach to teaching and in particular to bridging the gap between these two disciplines and in fostering collaboration?
Well, it's going to be a similar answer in a way that if we have limited resources, we don't have the possibilities to have any gap in between different jobs. The architect has to think how he's going to build the building, and the engineer has to provide the best answer for the architect. So they have to work together to find the best answer, because we don't have the choice at the end. We don't have the choice. And it's true that in the 20th century, some people thought that, well, if we consider that we don't pollute and we have unlimited resources, then it could be two completely separate jobs. The architect could draw anything and the engineer will build it. But in the context of limited resources, we have no choice to work together.
Absolutely. Thanks, Olivier. Well, you've raised some very big questions there, and plenty for us to dwell and digest on in terms of your presentation, and also really important themes which should be taken forwards to the IASS 2021 conference. Thank you very much for joining us on the Movers and Shakers interview series today. It was a real pleasure to talk to you and really enjoyed your presentation. Hopefully we can catch up with you again on the series as we move closer to August 2021 and the conference itself. But for now, thank you for taking the time to speak to us today, Olivier. Thank you very much.
Thank you very much, Mark. Thank you. Bye.